Okay, the question I received was how to calculate the original cell density of a liquid using a serial dilution and plate count. So imagine I have a bacterial culture in a tube. Okay? And this is a liquid culture, so there's some kind of liquid here, and there are bacteria in there. And for argument's sake, just now I'm going to just put them here as blue dots. Okay. And the question we ask ourselves is, how many bacteria are in this liquid? Bacteria in a liquid are expressed as the number of colony-forming units per milliliter of liquid. That is what we use to express cell density. And a colony-forming unit is the number of bacteria it takes to form a colony on a plate. So imagine I have this plate, and imagine that is circular, and that there are colonies on this plate, kind of like that, right? Each of these colonies is a colony-forming unit. That is the full name. The idea is that we may assume that each colony starts from one bacteria, but you already know that not all bacteria are all by themselves, that most bacteria are in some kind of arrangement. So you can have, for example, diplococci or tetrads or streptococci. That means that the bacteria naturally clump together in these larger groups. And each of these larger groups results in one colony. So this colony here it is right now visible to the naked eye. It is billions of bacteria, but it started from one little group of bacteria that is characteristic for that particular kind of bacteria. And so in the case of some bacilli, that can maybe one bacillus, but in the case of tetrads, it would be 4 cocci, or in the case of diplococci, it would be 2 cocci. And because that number of starting bacteria for each colony differs, that's why we call this a colony-forming unit. Okay, so the colony-forming unit is each colony-forming unit is the number of bacteria it takes to make one colony on a plate. So in this case, you might say I have 1, 2, 3, 4, 5, 6 colony-forming units on this plate. So that is what we're going to do. We're going to express the cell density of this original culture, and that is then called the original cell density, is going to be expressed as the number of colony-forming units per milliliter of liquid. Now, there are different ways we can do that. There is a machine you can use, a spectrophotometer, that you can stick this in, and that really calculates, this machine. Let's put it over here. You put the little tube in there with the liquid, right? And then this machine shines light through, and then it measures how much light is coming out on the other side. And because there are bacteria in here, not all of the light passes through. Some of the light is absorbed by the bacteria and either taken up or just sent back that way. And so the machine knows how much light goes in, measures how much light comes out, and the amount of light that is not coming through is a measure of how many bacteria there are in there. But not always do we have this spectrophotometer. And the other disadvantage of a spectrophotometer, so I guess one disadvantage is you need to have the machine, and the machine is, expensive. You need to have a culture that is relatively thin. So it cannot be a very dense colony. It's a very dense culture, I mean, because what happens is that if you remember what happens in a bacterial growth curve, right, is that the number of bacteria increases, then eventually flattens out, right? So if I leave this culture sit for a really long time, I get the number of live bacteria in this culture is not actually changing, because here I have as many bacteria dying as bacteria are dividing. The thing is that both dead and live bacteria um, will absorb light. So at low densities, as long as you're in this area, not a problem, and the spectrophotometer is a good measure of how many bacteria there are in there. But the more you're in this area of the growth curve, the less accurate the spectrophotometer is going to be, because the spectrophotometer will count absorption from both live and dead bacteria, and we are interested in how many live bacteria are there. Okay, so now that we've covered that, so let's now talk about and erase all this. Is there a way that I can, let me just go to a new page here. Okay. Okay, so let's go back to our liquid culture. We've decided that it's super dense right now, and we cannot really use the spectrophotometer, or maybe we don't even have a spectrophotometer, and we have to find another way to determine the original cell density of this particular bacterial culture. And so how can we do that? Now, because we know that each of these bacteria here is, at least in theory, a colony forming unit, you could just, take a plate of medium and pour like 1 milliliter of this culture over that plate, spread it out, and then put it in the incubator and incubate at 37 degrees Celsius, which is 98.5 degrees Fahrenheit. Right? Let that sit overnight and come back the next day, and then you can count the colonies. Right? And so each of these colonies is the number of colony forming, is a colony forming unit. And so we know we put 1 milliliter of this culture on this plate, we count the number of colony forming units. So let's say the number of colony forming units here would be 64. Then we can say there were 64 colony forming units in that 1 milliliter of liquid. And so the original cell density would be 64 CFUs per milliliter. Would be nice if we could do that. The reality is different. First of all, 1 milliliter is way too much liquid to pour over a plate. Okay, it becomes just this messy, watery liquid. So we can't do that. Typically, we spread maybe a tenth of a milliliter or a 20th of a milliliter. So 1 milliliter is actually equal to 1,000 microliters. So typically, we spread on a plate like 100 microliters or 200 microliters. Anything more than that is going to be hard to sustain. So this method, although in theory it sounds practical because it gives us right away the number of colony forming units per milliliter, doesn't work out. A milliliter is too much liquid. The other problem we have is that if for most dense cultures, if you put that in here, you won't actually be able to see the individual colony forming units, because there will be literally thousands of, in tens of thousands of bacterial colonies all over this plate. You can't tell them apart. So that means that if it's that busy, that would be what we call too numerous to count or too many to count. So then we can't figure out the cell density either. We've got to come up with a different mechanism. So the mechanism that we use to determine this is called a serial dilution with plate count. With plate count. So let's go check that out. We are starting again with our liquid culture. right? And there are bacteria in there, and we don't know how many there are. So what we do is prepare a serial dilution. And there are different ways to do a serial dilution, and there is a general formula that we typically use, and I'll explain that to you, and then I'll explain you sort of give a specific example. So in general, we dilute the culture by mixing it with either sterile water or with sterile medium, like a liquid medium, like for example, tryptase soy broth, TSB is a medium that we often use. But for argument's sake, let's just call it water today so we don't have to talk about medium. So we'll make a dilution of bacteria in water, and then we're going to take a sample of each of these dilutions and put them on a plate. So to make a serial dilution, whatever volume of water you're going to have in here, you put 90% of the total volume that you want in each of these tubes. So if the total volume you want is 1 milliliter, so 1,000 microliters, you would put 900 microliters in each of these. If the total volume you want is 100 microliter, you would put 90 microliters of water in each of these tubes. So in our case, because we've decided that 1 milliliter is too much, we're going to put 100 microliters in there. The other thing you can do is you can make a serial dilution with 1 milliliter and then only plate 100 microliters of that. But for argument's sake, let's just now start with 100 microliter total volume for each of these tubes. Okay. So that means I am going to put 90 microliters of water in each of these. Here we go. So 90 microliters of water here, 90 microliters of water here, 90 microliters of water here, and here, and here. Okay. Then for the first dilution, I am going to take 10% of the total volume. So I'm going to put 90% of my solvent, in this case, sterile water. All right. And then I'm going to put 10% of the volume of my the liquid that I want to dilute. And I'm going to start by taking then 10 microliters of this culture here that I want to figure out, right? And I add it to this tube, like the first one. There we go, like that. And then in reality, what you do is you mix it in, and so it all becomes mixed in there. So now the total volume is then 90 microliters of the water that I had in, plus 10 microliters of the original culture. And the total volume is 100. Okay. So that total volume of 100 microliter consists of 10 microliter of original culture and 90 microliters of water. That means I have 10 microliters of original culture in a 100 microliter total volume. That means however many microbes I had per milliliter here, right? I take that and 10 microliters of that in 100 microliters. So this is the same as 10 over 100 is 1/10. So however many microbes per milliliter I had here, I now have 1/10 of that in this tube here. And this is what we call the 10 to the minus 1 dilution, right? Because 1/10 is 10 to the negative 1. That should bring back happy memories of Algebra 1. Then in the second step, now I had added 90 microliters of water to each of these. In the second step, I'm going to take 10 microliters from here and move it to the second tube, okay, like that. And then I'm going to mix it in, right? And so now I have 90 microliters of water in this tube, plus 10 microliters of the 10 to the negative 1 dilution for a total volume of 100. So here again, I have made a 10 in 100 or 1 in 10 dilution, but I've made a 1 in 10 dilution of this first tube here, which was already a 1 in 10 dilution. So I've made a 1 in 10 dilution of a 1 in 10 dilution, which is a 1 in 100 dilution, which is 10 to the negative 2. So this tube here then becomes 10 to the negative 2. Then we keep going. Why stop there? So now we take 10 microliters of this tube and move it into that one for, again, 100 microliters in total. So this again is a 10-fold dilution, like 1 in 10 dilution, and it's a 1 in 10 dilution of the 10 to the negative 2. So by the same argument that we did before, this becomes a 10 to the 3, and hopefully you see a pattern. So now I'm going to move 10 microliters there, 10 microliters there, right? And so I'm going to get a 10 to the negative 3, 10 to the negative 4, 10 to the negative 5. And you can go on. When I used to do this back in the olden days when I still worked in the lab, I went all the way to 10 to the negative 9 because my bacterial concentrations were super concentrated. So this is what we call a serial dilution. So a serial dilution is this group of tubes. Each one of them has 10-fold less bacteria than the one before. And the reason we do this is we don't know how many bacteria are in the original. So by doing this, we're trying to find a culture that is going to give us a countable plate, because if we just did the original, it would be too many to count. So once we've made the serial dilution, and after every time that we've mixed in bacteria, we mix it really well, then we go out and we plate bacteria from each of these tubes, and we put that on an agar plate. Okay, I won't bore you with the details of the kind of medium that we use. But in this case, you can see that each of these has 100 microliters. So I can take the entire 100 microliters of this tube and pour it on the plate. Okay, so I'll label each of these plates. So I'm going to here put the sample from the 10 to the negative 1 tube. This is going to be the 10 to the negative 2 tubes, 10 to the negative 3, 10 to the negative 4, and 10 to the negative 5. So I take all of the 100 microliters of this liquid, I spread it over here. Okay, like all over. We have a special spreader, cell spreader that we use that will evenly spread this liquid over the entire surface of the plate. Okay, and you do the same over here. So this is the contents of the 10 to the negative 2 comes here. The contents of the 10 to the negative 3 plate, the tube go here. The contents of the negative 4 plate goes there. And the contents of the negative 10 to the negative 5 plate goes here. Okay. So we spread all these liquids evenly over the surface of the plate. So this guy goes there, that one goes there, this goes there, that goes there. So the entire content, all of the 100 microliters of each of these is spread over here. Then they're incubated. So we incubate this at 37 degrees Celsius overnight, and then you come back the next day. And most likely what you will find is that the number of colonies on this plate, and I'll put it in blue just to make it more visible, and let's make it nice and thick. Let's see if I can make it big. Here we go. Most likely you will see that this is going to be too many to count. You won't be able to see it. Okay. But this, you might see, it's maybe too many to count, but it may be not quite as dense. And here you might be able to see individual colonies, but still probably too many to count. They're all on top of each other. If it's so dense, you run several problems. Is that you can have two colonies right on top of each other and count them as one, so that's not accurate. And because if there's so many colonies on there, you will lose count, and then it's no longer accurate. So you need to find a plate that is going to have a countable number of microbes. So, and because each of these plates has 10 times less microbes than the previous plate, right? It's going to get a little less every time. And I could go on and make more dilutions, and every time it would get less and less and less. So which one of these can you use, can you count? This brings us with the concept of a countable plate. A countable plate is a plate that has between 30 to 300 colony forming units per plate. More than 300 is considered too numerous to count or too many to count because you're going to lose track. And less than 30 is going to be considered too dilute, and so the statistical error is going to be too great. This will not give you an error, an accurate result. So you don't want to count this plate here, for example, because it has only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 colony forming units. That's no good. That is less than 30. But this one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Anyhow, let's imagine, I'm too lazy to count. Let's imagine there are 42 colony forming units, because 42 is the answer to life, the universe, and everything. So 42 colony forming units on this plate. How can we use that information now to figure out the original cell density? Now we know that this plate was 10 to the negative 4, so that is a 1 in 10 to the 4 dilution, or 1 in 10,000 dilution of our original culture. So each of these has 10 times less bacteria. So whatever number I had here, I would have expected 10 times more on here, and 10 times more than that than here, and 10 times more than that on here. And then this would give us the original cell density. Okay. So in this case, so I had 42 colony forming units in what volume of liquid? We didn't plate a milliliter here. We plated 100 microliters there. That is a tenth of a milliliter. So we'll put it like 0.1 milliliter, right? So that means that per milliliter, if there's 42 colony forming units per 0.1 milliliter, that means that would be 420 colony forming units per milliliter. Now, although that is mathematically correct, scientifically this is not correct. And the reason for that has to do with significant digits. So we only counted 42 colony forming units, so that is 2 significant digits. But if I write 420, that is actually 3 significant digits. So a better way to write this would be 4.2 times 10 to the 2 colony forming units per milliliter on the 10 to the negative 4 plate. So this, let me put that in here in blue. This is sort of important. The 10 to the negative 4 plate, the concentration of the liquid that I poured on the 10 to the negative 4 plate is 4.2 times 10 to the 2 colony forming units per milliliter. And this is again just algebra. 420, I wrote that as 4.2. This is 2 significant digits, so yay, that's what we needed. But to make it 420, I add this multiplier, because to get to this number, to get to 4.2, I divided that by 100, so I have to multiply it again by 100 to get the same number. So 4.2 times 10 to the 2 is the same as 420. Okay, well, that's nice. Well, that was on the 10 to the negative 4. So I don't want to really open a new blank page, so I'm going to carve a little corner out here to do a little more. So the tube here that I used, the 10 to the negative 4 plate, right, had 4.2 times 10 to the 2. Oh, I'm not doing a very good job writing here. Let's try that again. So the 10 to the negative 4 plate had 4.2 times 10 to the 2 colony forming units per milliliter. But we are not interested in how many colony forming units per milliliter there were in the 10 to the negative 4 plate. We wanted to know that original cell density. Now, we also know that the 10 to the negative 4 plate, that is, 10 to the 4 times more dilute. So the original cell density would then be 4.2 times 10 to the 2 times 10 to the 4, right? To give it back to the original cell density. So that is per milliliter. That is 4.2 times 10 to the 6 colony forming units per milliliter. Why did I multiply by 10 to the 4? I multiplied by 10 to the 4 because I divided, so I diluted 10 to the 4 to get here. So now I have to bring it back to the original cell density. So the original cell density is then 4.2 times 10 to the 6 colony forming units per milliliter. I hope that I made that a little more clear. If not, go ahead and put some questions in the bottom here and I'll try to answer them.